Okay, hey folks, we're getting into this new module on kinetics. I'm really excited about this stuff. I've used kinetics quite a bit in my research here as well as in graduate school, so I'm super pumped that we're getting into this. So for this first learning goal, keep it pretty simple. Know how to calculate reaction rates for a gas phase or solution phase reaction and their respective standard units. Okay, so let's first by setting up our definition for a reaction rate. So you'll often see people write just rate to denote the rate of a reaction. And I'll give you the full correct definition. This is technically 1 over the volume times dz by dt. So, and if you recall, if we look at the change in number of moles of chemical species J, that was equal to its stoichiometric coefficient times this extent of reaction quantity. So if we want to know what just dz is, you can see that's going to be the change in number of moles of J divided by the stoichiometric coefficient. So recall for a simple reaction like the following, the stoichiometric coefficients for A would be -1, and the stoichiometric coefficient for B would be +1. Right? If there was a 2 in front of the A, it would be -2, and so on. So now continuing along with this, we can write that as rate equals 1 over volume times 1 over the stoichiometric coefficient times the change in number of moles of species J divided by some change in unit time. Okay, and then now finally, if we consider that the number of moles divided by the volume equals concentration expressed in moles per liter, we can finally see a good definition for rate here as 1 over the stoichiometric coefficient times dJ by dt. Okay, so let's box that off. Oh, excuse me, I'm not going to edit that out. Okay, so now if we look at this graph here, we've got concentration on the y-axis and time on the x-axis. So you can see reactants will decay and products will evolve. And if we look at any point along these lines here, the tangent will give us the slope, which is the same as the rate, right? It's the change in concentration over the change in time. But you'll also notice, depending on where I pick, in my time profile, I would get a different slope and thus a different rate. So we're going to have to figure out how to deal with that. All of the same now, the easiest way that we can calculate a rate is under the approximation that dJ will just be equal to delta J and dt will be equal to delta T, or another, and put that in a box for concentration. So in other words, that will be the final concentration minus the initial concentration divided by the change in time over that same window. Okay. So in gas phase reactions, the standard unit for concentration is molecule per cubic centimeter. Thus, the standard rate unit is going to be molecule per cubic centimeter per unit time. So I'll write seconds there for now, molecule per cubic centimeter per second, but it doesn't have to be per second. The only thing that's standard is the molecule per cubic centimeter. And as we'll see later on, as we keep going down this material, the molecule per cubic centimeter is very convenient for gas phase reactions. So how do we get that? Well, remember the ideal gas equation, PV equals nRT. So the quantity we're interested in calculating is N over V, which will equal P divided by RT. And if we plug in 1 atm for pressure, and we use our standard value for R, 0.08206 liter atm per mole K. And if we do this at 298 K, we get the following. So that ends up being, to 3 significant digits, 0.0409 liter per mole. That's mole per liter. I was so used to thinking about our partial volume stuff we were doing earlier. Mole per liter. So now, how do we get that into molecule per cubic centimeter? Well, we've got to do some good old-fashioned dimensional analysis, right? So in 1 mole, we know that there's an Avogadro's number of molecules. So that's 6.022 times 10 to the 23 molecules. And then we know in 1 liter, there's 1,000 cubic centimeters. So we get to what I think is a very famous number, 2.46 times 10 to the 19 molecules per cubic centimeter. And so why is that number famous? Well, that is our molecular density at 1 atmosphere. So by saying 1 atmosphere, it's the same thing as saying 2.46 times 10 to the 19 molecules per cubic centimeter. And that's convenient because if we adjust the pressure in powers of 10, all we have to do is adjust this number in powers of 10. So it's convenient to have it in that unit. Okay, so standard solution phase units, as you might have guessed, are in mole per liter. So not a whole lot to discuss there, other than that our rate will be mole per liter per second, or any unit time. So it could be mole per liter per hour, mole per liter per year, whatever is appropriate depending on the speed of our reaction. Okay, so we'll do a couple sample calculations for using these concentrations in both the gas phase and the solution phase during our live lecture. I'll see you then.